My name is Ishal Abdul Halain. Welcome to my video on the decrement and branch on condition codes instruction. Part 1. Let's begin. All of the instructions in the DBcc group uses the value of a condition code to determine whether to branch or not. According to its flowchart, a branch is executed when the condition code is 0. When this occurs, a down counter attached to the instruction is decremented by 1. Any data register, DN, can be used as the down counter for the DBcc instruction. After it is decremented, the microprocessor will check its value. If the value is not equal to -1, a branch to a label is executed. This is what occurs when a branch is executed. On the other hand, if the condition code evaluated is 1, a branch is not executed. There are 14 instructions in the DBcc group. Notice that all of the instructions start with the letters DB. This stands for decrement and branch. The preceding letters tell us the name of what the instruction does. For example, DBGE stands for decrement and branch greater or equal. The microprocessor knows whether to branch or not by observing the condition codes, which are in fact Boolean expressions, as shown here. The terms in the expressions come from the condition code register's flags. The flags are C, N, V, and Z. As an example, for the DBGE instruction, the 68K will branch when its condition code, given by the Boolean expression N and V, ORed with N bar and V bar, result is a logic 0. It will not branch when it is 1. The general syntax for all DBcc instructions are DBcc, DN, label. DN is the instruction's built-in down counter, and it may be any data register. The value placed in it will be the initial value of the counter. By default, the instruction will treat DN as a word-sized operand. If you place the DBcc instruction in a loop, that is by connecting the branch instructions back to the DBcc instruction, the loop will run for DN plus 1 times. This is because DN is decremented until its value is equal to -1 before the branch is terminated. For example, if we initialize DN to 2, the loop will be executed 3 times, because DN must be decremented until -1 in order for the loop to be terminated. Another situation where the loop is prematurely terminated occurs when the last instruction in the branch instruction affects the status register such that the condition codes evaluated equal to 1. We will examine this condition in part 2 of this video series. Let's move on. Let's study the decrement branch equal instruction. This instruction first checks the Z flag's value. If the value is 0, a branch is initiated as shown in the flowchart below. It's exactly the same as explained in the previous slide. If Z equals 1, the branch does not occur. The general syntax is DBEQDN, label. As you might have guessed, the condition code checked for branching is only the Z flag. Let's look at an example on how the DBEQ instruction is used to implement a loop. Let's assume that this code shows the last 4 lines of a big program. Its flowchart is on the right. The first line we see is used to move a word with value 5 into D1. D1 will be the loop counter for our DBEQ instruction. The next instruction is not.bd0. It is attached to a label called here. When executed, it will change the status register as follows. The N and Z flags are affected, the V and C flags are reset to 0, while the X flag is not affected at all. The next instruction is our decrement and branch instruction. When executed, it reads the Z flag. To see the value of the Z flag, we will look at the previous instruction, not.bd0. If D0 is initially not equal to FF, then its inverse value after executing the not instruction is non-zero. This resets the Z flag to 0. The DBEQ instruction senses this, and decrements D1 by 1. The microprocessor then checks whether D1's value is equal to -1 or not. If not, a branch back to here is executed, and the process is repeated until D1 is equal to -1. When this occurs, the program will end. Now, let's consider the scenario when D0 is initially equal to FF. The Z flag is set to 1 because the inverse of FF in binary is 0. Thus, no branch is executed. Do you know how many times the branch is executed if D0 is not initially FF? Yes, 6 times. Recall that all DBcc instructions terminate when the loop counter is -1. In this example, our loop counter D1 was initialized to 5. Thus, the counter is decremented 6 times in order to arrive at -1. Therefore, if D0 is initially not equal to FF, the branch will be executed 6 times. Now let's develop a program using the DBeq instruction. We will call this example program, loop rotation. It's going to rotate data in a register 3 times to the right using the DBeq instruction. Here's the flowchart that shows the general idea behind our program. We will first rotate data to the right by 1 bit. Next, we check whether we have rotated the data 3 times or not. If not, we will branch back to rotate the data again. However, if the answer is yes, then we will end the program. This is the program that implements our simplified flowchart, and this is the flowchart of the program shown. It has 4 lines of instructions. The first 2 instructions are for this first process box. Move instructions are used to initialize the data we will rotate in register D0. A counter is set to 2 in register D1. Note that the operand size is .w for the second instruction. This is because .w is the default counter size for any DBcc instruction. The next instruction corresponds to this box. We will use a rotate instruction attached to label rep to rotate the contents of D0, 1 bit to the right. I chose the label name rep, which means repetition for short. The next instruction is our DBeq instruction. It corresponds to the decision-making box here and the 2 process boxes that follow. When executed, the DBeq instruction checks its condition code, which is the Z flag. If it is 0, a branch is initiated by decrementing D1 by 1. The value of D1 is checked. If it is not equal to -1, the program branches back to the instruction at label rep, and the process repeats. Once our counter is equal to -1, the program ends. However, if the DBeq instruction senses that the Z flag is 1, then the branch is not taken at all. The program just ends. Let's simulate our program. To the left of our code is the addresses associated with each instruction. Note that the instruction at address 1008 is attached to our label, rep. We have also set up the program counter, register D0 showing its first 8 bits, and register D1, for the loop counter. When the program is executed, the program counter points at the starting address, which is 1000. Before executing the first instruction, the program counter is incremented to point to the next instruction, which is at address 1004. Then, the instruction is executed. This causes 88 to be moved into D0. It is shown in binary, and it is the data to be rotated. The program counter is now pointing to address 1004. It is incremented to 1008 before executing the instruction it is pointing to. When the instruction is executed, 2 is moved into D1. It is the initial value for our down counter. The program counter is now pointing to address 1008. It is incremented to 1000A before executing the instruction it is pointing to. The rotate instruction is executed, and register D0 is reconfigured for the rotation to take place. The C flag is attached to the LSB of D0. The C flag is also connected to the MSB of D0. Note that the value of the C flag is 0. This is because the previous instruction was a move instruction. After executing a move instruction, the 68K always sets the C and Z flag to 0. OK. Then, the data in D0 is rotated to the right by 1 bit. After this, the 68K updates the condition code register as shown. The X flag is unaffected. All of the other flags are reset to 0. The program counter is now pointing to address 1000A. At this address, we have our DBeq instruction. Once DBeq D1, wrap is executed, it checks the Z flag. Since it is 0, a branch takes place. The branch starts with a decrement in D1's value by 1. Then, the 68K checks the value in D1. Since its new value is not equal to -1, the program counter changes and points at the label wrap, at address 1008. The program counter is now pointing to address 1008 because we have branched back to label wrap. The program counter is incremented to 1000A before re-executing the instruction it is pointing to. The rotate instruction is executed and the data in D0 is rotated to the right by 1 bit, and the status register changes again as shown. The program counter is now pointing to address 1000A. Since the Z flag is 0 due to the previous rotate instruction, a branch will take place when the instruction DBEQ is executed. Data register D1 is decremented by 1. Since its new value is not equal to -1, the program counter changes its value to point at the address of wrap. It points to 1008 again. We are back at address 1008, the program counter is incremented to 1000A before re-executing this instruction for the third time. The rotate instruction is executed and the data in D0 is rotated to the right by 1 bit, and the status register changes as shown here. Note that the new value is non-zero, thus, the Z flag is reset to 0. The program counter is now pointing to address 1000A. Since the Z flag is 0, a branch is supposed to take place when the instruction DBEQ is executed. Upon executing DBEQ D1, wrap, data register D1 is decremented by 1 as usual. However, its new value is -1. Thus, the program counter changes its value to point to the next instruction at 100E. The program does not branch back to wrap. The program simply ends. This is how the DBEQ instruction can be used with the rotate instruction in order to rotate data 1 bit at a time. It uses the Z flag and register D1 to determine whether to rotate or not. Hopefully by now you would have understood how the DBcc instruction works. Be sure to tune into part 2 of this video series. There, we will look at another detailed example of another DBcc instruction in greater detail. Thank you, and have a nice day.